Okay, folks, in this video we're going to use implicit differentiation technique from section 3.5 to find the derivative of a inverse trig function. In this case, we're going to do inverse sine function. All right. So this derivative is given to you in the book. It's on page 214, and they actually just give you the derivatives kind of straight out of all 6 inverse trig functions, okay? They give a little bit of explanation, but kind of lacks a lot of it. So what I'm going to show, I probably wouldn't ask you to recreate this because it's pretty long. It's a good review, though, of what inverse trig functions mean in the first place. And it's good practice doing implicit differentiation, the general technique. All right, so I'm going to run through it. But again, the derivatives are posted in the textbook, so you've got them there, okay? Section 3.6, we use the same technique that we're going to use here, implicit differentiation, to find the derivative of natural log of x. And that one's a little bit more straightforward, so it's still an example of using the implicit technique. This one goes a little overboard because I'm going to be using unit circle, right triangle, lots of sort of trig review. So let's go in here. First of all, what do these things mean? What does this mean? So these two notations mean the same thing. And if we see y, arc sine of x, or sine, the inverse sine, I read this, of x, that means that sine of y is equal to x. All right, so this is true if this is true, and then there's a certain couple of restrictions on that. All right, what does that mean? Well, let's just think about what sines are, or trig functions in general. So sine, usually the input of a trig function is an angle. So sine of some, I'm going to use kind of this little angle symbol. So sine of an angle equals, and I'm using a little number symbol, just some kind of number, some kind of value, right? And you might say, well, wait, angles are numbers also, right? We represent angles with numbers, which is true. But we think about specifically that the input of these functions are angles, and then the output is just some kind of value. So in other words, if I say sine of, let's say, 30 degrees, then the answer to that, the value, the number associated with that is 1/2. Okay, so then if we convert that or try to make this statement using an inverse sine function, we can say arc sine. So arc sine of the number, now 1 over 2, 1/2, is equal to some angle. So I read inverses a lot, almost like a question. So in other words, if sine of 30 is 1/2, then arc sine of 30 is saying what is an angle whose sine is 1/2? And then the answer to that is 30 degrees. Okay. So that's the answer to the value for this inverse function. That's one answer to the question I asked, though. So you might be thinking back to trig and saying, wait a minute, sine is a periodic function. It's an oscillating function, right? The graph is a wave. And so if I graph the wave of sine in both directions and say, where is that function hit the height of 1/2, right? Well, there's an infinite number of solutions. This is one of them right there. And that's the one we just found. That's my 30-degree mark right there. But right there is another solution, right? That would be 150 degrees. If I come all the way over here, that would be 360 plus another 30, so 390 degrees, right? There are solutions going backwards. So there's an infinite number of angles whose sine is equal to 1/2. And so if we want to have a well-defined inverse function, a function can only spit out one answer, right? There can only be one angle to answer this function. And so what we said back in pre-calc is we said, well, we've got this sine function that's not 1-to-1. It's repeating itself over and over again. But let's sort of truncate it. Let's cut it off. So it comes up to this height, this maximum height, let's say of 1, right? And that happens right here at the angle pi/2, or at 90 degrees. And it has its minimum, the height of -1, right here at -pi/2, or -90 degrees. All right, and so what we do is we restrict the range where these angles might live. We restrict that range and we say, okay, I want to know an angle whose sine is 1/2, but it has to live in that interval. All right, it has to live in that interval. Here, y is representing the angle in this expression because y is the input of my sine. So where y, and we're just going to bound this between -pi/2 and pi/2. Okay. That's an important detail when it comes to defining inverse trig functions. Okay, so that was important way back when in pre-calc. It's going to sort of be important here in some of the work we do because we're going to sort of solve for something and we're going to need to know that that's true about y. So when that comes up, I'll make a note of that. And also, let me just mention this derivative that we're trying to find here and the fact that this interval is sort of critical for inverse trig, in particular this inverse sine function, This idea gets used a lot in Calc 2. So we're introducing it in Calc 1 because it falls under the implicit differentiation sort of umbrella is the technique we're doing. Then there's a few exercises where you need to know what these derivatives are. But you will use these derivatives a lot in Calc 2. Okay, so if you don't believe me, email me next semester and say, yeah, we're using this all the time, probably about halfway through the semester. All right. And there's a proof where this little detail comes into play. Okay, back to the problem at hand. So what we've done so far is, if you're a unit circle type like I am, let me just mention what this interval looks like in the unit circle. So if 0 radians or 0 degrees is here, then if I rotate up 90 degrees, I hit pi over 2 up top. And if I rotate backwards 90 degrees, I come to negative pi over 2. So what we're saying is the angle that I'm looking for that would be my answer to an inverse trig problem has to live sort of in this rotation, so through quadrant 1, or backwards through quadrant 4. And those are the same angles that I just had on my little truncated sine graph, that wave graph where we cut off. That's quadrant 4 angles, quadrant 1 angles. So there we go. All right. So in pre-calc, if you had me, I used to call this thing the band, right, or the little stripe. I find that useful. So let me put my little unit circle right there and kind of just highlight the little strip or the little band along the unit circle where any of these angles will live. Okay, so that helps me visualize, and maybe we'll come back to that towards the end of this. Okay, so back to the problem at hand now, finding the derivative now of this function. So we want to find the derivative of this thing, arc sine of x, but I called arc sine of x y. So that means I want to find the derivative of y, right? So we want to find y prime is how we call the derivative of y, or we might want to call it, to be specific, since y is a function of x, we want to find dy dx, right? So we can use either, I guess this notation will pop up first in our work, and then we might want to call it y prime now, just to be a little bit more concise, okay? But that's our goal. That's what we're trying to find. So the idea of using this expression, which means the same thing as our inverse function, is now we can use the idea of implicit differentiation. In other words, I'm just going to apply, I'm looking for a derivative with respect to x. So I'm just going to apply d dx to both sides of this thing. And then that's going to introduce at some point a dy dx, and then, or y prime I can call it, and then I want to solve for that piece, and then I'm done. Then I found y prime, I found the derivative, okay? So let's apply d dx to both sides. So d dx of sine of y is equal to d dx of x. All right, so just to reiterate what we're doing, if sine of y equals x, that means they're the same, right? They mean the same thing. So this means the same as that. Then if we do the same thing to both sides, we'll get the same result. So we're differentiating both sides with respect to x here, okay? This becomes a application of the chain rule. Why? Why, right? Kind of a pun. Why is that true? Because I have a function of y, right? I don't have a function of x, but I'm trying to take the derivative with respect to x. So the way I can figure out what to do is if I'm trying to take a function with the derivative with respect to x, but I've got a function of y, then the first thing I need to do is take the derivative with respect to y, right? I need to take the derivative with respect to what I'm looking at. So what I need to find is d dy of sine of y, right? And then what we do is we multiply that by, well, I want a dx in the bottom, right? That's what I'm supposed to be finding. So we need some kind of dx. And now we introduce this dy down in the bottom, but if I put dy right there, now that cancels, right? So again, that's just a application of the chain rule. So we apply the chain rule right there. And on the right-hand side, dx of x, another way to sort of write or phrase that is dx over dx, right? So as a fraction, you would think that ratio is 1, but the derivative of the line y equals x is a 1. Okay, so we just get a 1 right there. All right, let's keep going. So now we want to take the derivative with respect to y of sine of y. So we know the derivative of sine is cosine. Our variable here is y. So we end up with cosine of y times, you could keep calling it that, dy dx. It's a little bit shorter maybe to call it y prime. And that's our goal. So we've introduced it. Now what we need to do is solve for it. All right, and we've just got the constant 1 over here. So for the moment, I can solve for this. I can say y prime is equal to, and what I'm going to do is divide both sides through by this cosine term, cosine of y, and so I've got 1 over cosine of y. 1 over cosine of y. All right. So we're almost done here, except my original function is a function of x, right? And so its derivative, I want it to be a function of x. I don't want a y here. It's not going to be helpful. So I need to somehow look at some kind of information we have on the board and figure out how to replace cosine of y with something to do with x. Okay, and so that's going to rely on the use of a right triangle. All right, so I got to be a little bit creative here. I'm going to take this statement and interpret that on a right triangle and go from there. Okay, so we found the derivative, so all this work I can get rid of for now. And let's see what we've got going on. Okay, so at some point, I guess I got to mention this. Let me mention it now. The fact that our angle here, y, lives in quadrants 1 or 4, that means cosine is positive. So cosine, or non-negative, I should say. Cosine of y is greater than or equal to 0. Why is that? So let's just think back to what cosine means. On our unit circle, cosine is the x-coordinate of whatever point we land on when we start rotating. And so if I start rotating in quadrant 1 or in quadrant 4, the x-coordinate is always positive, right? All these x-coordinates over there are positive. And so since cosine of the angle, and here y is really just the angle that's happening inside of there. How do I know that? Because it's sine of an angle. And so cosine is going to be a non-negative value here. Okay, you can kind of get away with this now without doing that, except how can I say that? Well, we'll see. We'll see. We're going to be solving a radical, and then so a plus minus pops in, and we want to disregard the minus, and that's why, because we're going to claim that we're positive. Okay, so what do I mean? We're going to get a radical going. Sine of y equals x, right? And for the sake of this argument, I'm going to call that x over 1. Why am I going to do that? Because we know so, ka, toa, right? That's basically our definitions of sine, cosine, and tangent, right? Sine is the ratio of opposite over hypotenuse. So here, y is representing an angle here. To form a ratio, I have x. I can always call something itself over 1, so we'll do that, okay? So we know sine of y is equal to x over 1. Let's set up a triangle and then figure out what cosine of y is going to be equal to. All right, so I'm just going to draw some kind of arbitrary right triangle right here. And let me draw a angle, one of the acute angles, and I'm just going to call that y. So sine of y is x over 1. So that means the opposite is x, and the hypotenuse has length 1. Okay, so I mark up this, this right triangle like that, and what I want to figure out now is what's cosine of y. Okay, fair question. So cosine is the ratio of adjacent over hypotenuse, right? So the hypotenuse here is just a 1, so we're just dividing by a 1. So really cosine is going to be whatever the length of this adjacent side of the right triangle, right? The side adjacent to my angle y. And so I need to figure out what that is. So let me call that, let me call it a for adjacent, right? I could call that whatever I want. So I need to solve for a. Okay, Pythagorean theorem says a squared, which I called it a, plus b squared, that side length squared, so x squared, equals 1 squared, right? 1 squared, and 1 squared is just 1. So let's solve this for a. So 1 squared is 1, subtract x squared, so I get a squared is 1 minus x squared. And now is where this little caveat that cosine of y must be a non-negative number is going to come into play. Because technically, when I square root both sides here, I'm going to get that a is equal to plus or minus square root of 1 minus x squared. All right, so technically speaking, that plus minus happens. However, our cosine now, cosine of y is adjacent a over 1, right? A over 1, which is just a. So cosine of y is a. We know that cosine is not a negative number. This radical is going to produce a positive number, so we can get rid of the minus sign. Okay, so a little detail kind of to worry about, but get rid of the minus sign. If we got rid of the minus sign, we don't really need the plus sign to show that it's positive because square root will be positive. All right. There we go. So a is that, cosine of y is that. So we've shown that cosine of y, let me see if I'm in the reflection over here, cosine of y is equal to square root of 1 over x squared. Cool. Now we're done, right? Now we can finally tie this whole idea together. So y prime which again is the derivative of y. So the derivative of arc sine is equal to 1 over cosine of y. Cosine of y is this radical, and so we get 1 minus x squared. Okay? Kind of let out a deep breath. I'm going to let out a deep breath because that was kind of a big, long process, right? Kind of a lot of different stuff going on. A lot of review, unit circle, right triangle. There we go. All right. So let me just kind of clear this up as a rule. State this as a rule here. Let's just say instead of calling it y prime, I can say the derivative with respect to x of arc sine of x is equal to that expression right there. All right. And if this said the derivative with respect to x of inverse sine of x, still equal to that, right? Because these things mean the same thing. All right, there we go. Could you do something similar with the arc cosine? Yeah, so you could work it out. The other one that's worked out in the book is arc tangent, okay? Because that one works a little bit differently. Same idea. So let me look at that, see if it looks worth doing. But what you're going to want to do essentially is find all of these printed in the bottom. I'm definitely not going to do all 6. So look on page 214. They kind of show you the technique for sine, show you the technique for tangent, and then throw the rest at you and say, here. You know, there you go. There's probably some exercise in the book to prove the rest. But anyway, there we go. That's the derivative. And just to reiterate one more time, really important once you get to Calc 2. All right, you'll see that. You'll use that often.